Hello everyone, this is Dr. Webb and welcome to the very first video for Abstract Algebra 2. In this video we are going to start looking at a very important classical question that really is really going to the heart of a lot of what we're going to be working on this semester, and basically it boils down to trying to find and understand solutions to polynomial equations. In this video specifically, we're going to look at some very old historical stuff. In particular, how to solve quadratic and cubic equations. Some of this will be review, and some of this will probably be something that you haven't seen before. So here we have a basic polynomial equation. So for us, these coefficients, these a n here's, are all going to be from a field, and also particularly for us, normally these are going to be real numbers and in fact usually rational numbers. But for right now, we can think about these a n's as being real numbers. And so one of the things we know about the real numbers is that they are a field. And so all of these numbers, this first one in particular, a n, since it's the lead coefficient, we can say that it's not equal to 0. And so since we're in a field, that means that its reciprocal exists. And so we can take this polynomial equation, multiply both sides by the reciprocal, and what we end up with? We end up with this. And if you notice, the first coefficient has changed from a n to be 1. And so we've changed the lead coefficient to be 1. And this is something that we can do for any polynomial equation. And in fact, normally when we think about polynomial equations, we're going to be doing just this trick. And so polynomial whose lead coefficient is 1 has a special name. It's called a monic polynomial. So this right here is a monic polynomial, and any polynomial equation where the coefficients come from a field, we can just assume without really changing the equation that the polynomial involved is monic. So one of the big important results in algebra is called the fundamental theorem of algebra. It's something that we all kind of know and we hear about from at least high school. And it's that if you have a degree in polynomial with real coefficients, then it has exactly n roots in the complex numbers. And so exactly n roots, that means that we're counting multiplicities. If it has a double root, we count that root twice. If it has a triple root, we count that root 3 times. Okay, we're not going to prove this. The proof in this is actually fairly involved. And the first proofs and the ones that actually are easiest to follow use complex analysis, which is way outside the scope of this course. And so we're just going to take this as a fact. So this was proven right around the beginning of the 1800s. It was part of Gauss's dissertation, although he didn't completely solve it. And there was a similar but alternate proof that came out about 6 or 7 years later, and that one's usually the one that this is based on, but both of those were based on complex analysis. Now the one thing about these proofs, in fact pretty much all proofs of the fundamental theorem of algebra, is that they're non-constructive. And so what we mean by non-constructive is that it tells us how many roots there are, but it doesn't give us any way whatsoever to really find the exact values of those roots. So it says the roots are there, but it doesn't tell you how to get them in any way. And so how to find these roots, how to find these solutions to polynomial equations, the fundamental theorem of algebra tells us that they're there, but it doesn't tell us how to get them at all. So let's start with quadratic equations. So how to do this was known at least as far back as the Babylonians, and so that's more than 3,000 years ago, before the Egyptians, definitely before the Greeks. And so this was They would not have written the equations like this, but they would know how to solve them. And so here's our basic quadratic equation. So again, we're assuming that it's monic. And if you haven't seen how to get the quadratic formula, we're going to run through it right here. And so the idea is that we're going to set up using set this up as by completing the square. So first we move the L to the other side. And so we have x squared plus kx is equal to minus L. And then on the left side here, we're going to complete the square. And so recall that if we have something like x plus a squared, this is equal to x squared plus 2ax plus a squared. So this 2a here, we're going to call k, and if 2a equals k, then the a that we want to use is going to be k over 2. And so if a is k over 2, what's a squared going to be? That's going to be k squared over 4, and that's what we're going to add to both sides. Okay, and so we add the k squared over 4 to both sides. Now the left side with the x we can factor, and so this is going to factor to x plus k over 2 squared. Let's make that look pretty. And now we can take square roots on both sides and solve for x. So take square roots on both sides, move the k over 2 over to the other side, and we get that our solutions for x are minus k over 2, and then because we took the square root, remember there's both the positive and negative roots, so we get plus or minus square root of k squared over 4 minus L. And we start with a quadratic equation. It is degree 2, and so it has exactly 2 roots, and the formula here, we've gotten both of those roots. Okay, so now what about cubic equations? Okay, and so this is something that was solved at least by the Renaissance, by a mathematician slash gambler named Cardano. And so we're going to kind of go through his process on how to solve these. And so here we go. We're going to start off with a simpler case, and this is a case where there is no x squared term. Okay, and so we're starting off with there's just x cubed plus px plus q equals 0. Okay, so this is going to involve figuring this out is going to involve some change of variables. So the first thing we're going to do is we're going to set x to be the cube root of u plus the cube root of v. I know this seems like a random thing to do. It's going to end up working at the end. Really, it took people, the length of time between finding the solution to the quadratic formula to the cubic formula was about 3,000 years. And so lots of different things were tried in that time. And this really is the one that seems to work. And so if we set x to be the cube root of u plus the cube root of v, and we'll say what u and v are going to be later, then x cubed is going to be cubing that all. And if we multiply it out, we get u plus 3 times the cube root of u squared times v plus 3 times the cube root of u times v squared plus v. And that's just using the binomial formula. And then we're going to rearrange this. If you notice, from these two terms, we can pull out a 3 square root of uv from both of them. And so we can rearrange this. We're going to move the u and the v together, and then we've pulled out that 3 cube root of uv out of there. Okay, and so we're going to plug this whole thing, in for x cubed above, and then for px, we're going to plug in cube root of u plus cube root of v there. And we end up with this equation. And now, so this first term, this is all coming from the x squared. This is our px, and then q is still there. And now looking at this, we notice that this term and this term both have our x there, our cube root of u plus cube root of v. And so we can rearrange that and factor that out of those two terms. And so we have, and we're going to move the q over to the u plus v plus q plus, now factoring out, we have 3 times the cube root of uv plus p times, that was our original x, cube root of u plus cube root of v, and this is equal to 0. Okay, now looking at this, we have x. We can be pretty sure that x is not equal to 0. There's a possibility it could be equal to 0, but probably not. So if we had x as if x was a root by itself, we could have just factored that out from the beginning and ended up with a quadratic. So it's a reasonable idea to think about this not equaling to 0. But we know that this overall equation over here does equal to 0. So how can we make that happen? Well, what our goal is going to be, or what we're going to try and do, is we're going to try and pick our u and v to force this to equal 0. And the way that we're going to do that is we're going to break it up into 2 parts. The u plus v plus q, we're going to set that equal to 0 so that that part disappears. And then we're going to take this other factor that we're multiplying to x, this 3 times the cube root of uv plus p, and set that equal to 0 as well. And so if we can do that, if we can pick u and v to force both of those parts to be equal to 0, then we would have found a solution to the cubic. Okay, and so it's not that we have to do this, it's that if we can do this, it will work. So the u plus v plus q equal to 0, there's not much we need to do for that. So first we're going to focus in on that middle term right there. Okay, so if we set 3 times the cube root of uv plus p equal to 0, let's get rid of this cube root. And so we're going to move p to the other side and then divide by 3. And then we have the cube root of uv on the left. So let's get rid of the cube root. So we're going to cube both sides. And we end up with uv is equal to minus p cubed divided by 27. Okay, and so that's, if 3 times the cube root of uv plus p equals 0, then it must be that u is equal to minus p cubed over 27. Okay, so now we have the two equations we're looking at. U plus q plus v equal to 0, and uv is equal to minus p cubed over 27. And so at this point, we have really good hope that we can solve these. So if you think about q and p as being real numbers, then this first equation, this really is talking about a line. And then the second equation, u times v is equal to minus p cubed over 27, this is going to be a hyperbola in u and v. And so if you think about, the graphs of a line in a hyperbola, in general, a line will cross a hyperbola twice. And so it should be pretty straightforward at this point to get solutions. So how are we going to get solutions here? Well, there's lots of ways we can go. But the way that we're going to go is we're going to take this top equation and we're going to multiply everything by u. And so if we multiply everything by u, we get u squared plus qu plus uv equal to 0. And then we've forced this uv, and what do we know that uv is equal to? Well, it's equal to minus p cubed over 27. So we can substitute that in. And now we've gotten rid of the v, and what we're left with at this point, this is a quadratic in u. And so since it's a quadratic, we know the quadratic formula. We can just apply that here to figure out what u has to be. So by the quadratic formula, u is going to be minus q over 2 plus or minus the square root of q squared over 4 plus p cubed over 27. Okay, and then once we have u, Well, we know that u plus q plus v is equal to 0. And so that means that v is going to be equal to minus q minus u. And we know what u is. And so we can plug that in. And we get that v is equal to minus q over 2. And then instead of plus minus, it's going to be minus plus square root of q squared over 4 plus p cubed over 27. So now we know what u and v have to be. And so go back to original equation, x squared plus px plus q equals 0. Well, now we know we have a solution, x, where x is the cube root of u plus the cube root of v, where u and v are these values that we saw before. Now, if you think about the only difference between u and v is this plus minus sign. And so it might look like we have two solutions here, but really, if we swap the plus and minus, in both of them, it actually just permutes the two, right? And so really, there's just one solution here. So this is one solution. Changing these pluses and minuses just swap u and v, and so it doesn't really give us a new solution. But the fundamental theorem of algebra that we saw earlier says that a qubit is degree 3, so it should have exactly 3 solutions. So we have one of them here. What happened to the other two? How can we get the other two? The quadratic formula gave us 2 right off the bat. This is only giving us one solution. So how can we find these other two? Well, so let's think about a simpler cubic equation. Just t squared equal to 1. So I'm using t here so we're not confusing ourselves with x. Right? We know that one solution to this is 1. Right? So obviously if I plug 1 in here, that's a solution. So if I set 0 equal to t cubed minus 1, the fact that t is equal to 1 is a solution means that I can factor out t minus 1 from this. And if we do that, we get that t cubed minus 1 is equal to t minus 1 times, now we have a quadratic, t squared plus t plus 1. And if we apply the quadratic formula here, we get the other two solutions to this cubic equation. That's minus a half plus or minus cube root of minus 3 over 2. Or this is often written minus 1/2 plus or minus square root of 3 over 2i. Okay. So the plus on this is usually given a special name. This w here, really, this is a lowercase omega. And so omega is often given to this other cube root of 1. And then if we square omega, it turns out that gives us the minus sign, right? And so the 3 solutions to t cubed equal to 1 is 1 omega and omega squared. And those are our 3 solutions. And so what this is telling us is that when we take the cube root of something, so if we want t cubed to be equal to a, the 3 solutions to this are actually the cube root of a, which is the real solution, and then we have 2 complex solutions, which is going to be omega times the cube root of a and omega squared times the cube root of a. And so when we think back about, when we set x to be the cube root of u plus the cube root of v, there really are 3 cube roots of u and v to choose from. And so maybe it matters which ones we do. And so we found the solution using the real cube root. What about the 2 imaginary cube roots? Okay. And so really, does this equation have a solution where instead of, for the cube root of u, we're really using omega times cube root of u, and then we're forcing omega in here, and then is there some gamma here, where gamma is one of the other cube roots that makes this work? Okay, so if I force gamma to be, if I force when I take the cube root of u to get gamma times root u, what gamma would work here to make this also a solution to the same cube. And so if we go back in to where we started, plug these in for x, do the same things that we did before, we can rearrange it like this. And so you notice that we have u plus v plus q staying the same. We still get back the same x over here, but now this term that's getting multiplied x is changing some. Okay. And if we recall, what we did here is that we forced that part to be 0, and we forced that part to be 0. Now looking at this, p, this is a real number, because it's the p that we started off with. However, omega, this is definitely not real. It is a complex number, not a real number. But when we take these two terms together, they have to add up to 0, which is also a real number. And so that tells us that this term here has to end up being real as well. So what does gamma have to be to make this real? And it turns out that the only way it can possibly be real is if gamma, so we need gamma times omega to be real. And the only way this can possibly happen is if gamma is equal to omega squared. Okay, and so this gives us a new root. And so that would be omega times the cube root of v u plus omega squared times the cube root of v is equal to x. And we could do the same thing where we're starting off with omega squared instead of omega, and then it turns out that the term in front of v would have to be omega. Okay, and so that's how we get our three roots. So our three roots are cube root of u, the real cube root of u plus the real cube root of v. The second one is omega times the real cube root of u plus omega squared times the real cube root of v. And then the last one is omega squared times the real cube root of u plus omega times the cube root of v. Okay, so that was all for solving the special cube root x cubed plus px plus q equal to 0. How do we solve now a general monic qubit equation? So x cubed plus ax squared plus bx plus c. Well, if we set the cubic on the left, call that f of x, my claim is that I can shift this cubic to the left or right in some way to make it look like that case we had before. So really I can find some value for h that shifts this so that it becomes this form that we already dealt with. Okay, and so if you look at plugging in x minus h for x, and you go through, use your binomial expansions, expand it all out. I just did it all here. I didn't want to take the time writing it up, but it's a really good exercise, especially if you're a little bit rusty with the binomial formula. This is what you end up getting when you expand it out. And so we want this term with the x squared to disappear. And so what value can we pick for h to make that happen? Well, if we set h to be a over 3, then this term cancels off, and you get this, you get the other two terms. You get it in the right form once you plug all the numbers in, right? And so if we look at f of x minus a over 3, it's going to look like x cubed plus px plus q, where p is going to be b minus 2a squared over 3 plus a cubed over 3, and q is equal to c minus ab over 3 plus 2a cubed over 27. I think in terms of all of this, in terms of all these formulas, I think you're getting a sense as to why this is not usually taught in high school. There's a lot of variables going on. It's a lot of formulas plugging into other formulas. But really the ideas behind this are very classic. They're very classical. It's more involved than the quadratic formula, but it's very much in sort of a similar style. Okay, so now that we have this in this nice form, well, now we can find the roots of this cubic equation. And then to get the roots of our original cubic equation, we're just going to shift it back by the a over 3. So we're going to figure out the values of x minus a over 3 that make this equal to 0, and then we just add the a over 3 back into each of them to get our solutions to our original cubic. Okay, so we did this for the quadratic and the cubic. There is a similar but much, much longer process to find the roots for quartic equations. That would take quite a while to go through all of them, and so I'm kind of glossing over that. But there is a way to do it that uses very much the same ideas. It relies on both the quadratic formula and the cubic formula. And this was known back at the, around the year 1800, and even before that, that these could be done, since the 1600s. But using the same ideas, no mathematician at the time could figure out how to do this for polynomials of degree 5 or more. In fact, the strategy just completely falls apart. And rather than, if you remember for the cubic, we started off with a cubic, and then by using our clever change of variables, we were able to break it down into a quadratic equation, and then solving the quadratic was pretty easy. Similar to in the quartic, you use the same ideas. You take the quartic and you're able to break it down into solving some quadratic formulas and some cubic formulas, and that's how things go. But if you start off with a degree 5 polynomial, really any way that this goes, even if you are as careful as you can possibly be following the same ideas as this, you are going to end up with at least a degree 6 polynomial you have to solve. And so if you can't solve degree 5, then it's unlikely you can solve degree 6. And degree 6, it would get even worse than that. And so none of this same ideas work here. And so one of the ideas for this course and going through this course is to understand why these fail at degree 5. And in fact, why there can't be a general formula that works for degree 5 or more. That is all for this video. I will see you again soon.